Okay, so here's our picture. Now this matrix acts on vectors of length 3, so this is just vectors, this ABC is a vector in R3. So V is the same as R3, and we get vectors when we put different values of A, B, C in here. We get vectors over here that are members of R5. So that W is R5, and this then is, our matrix A then defines a transformation where we transform each vector in this space, which is R3, to get a vector in this space by the matrix A. Okay, so this is our row space. This is our null space. So I could call this is N of A, and this is what I've called row of A. The row space, which has dimension 3. It has dimension 3 because we fully expect that the rank of this matrix is 3, that when we reduce it, we'll get 3 non-zero rows. Again, because of the situation, because this being real-world data, and same y for every value, no t that's associated with 2 different values of y. Okay, so here's our familiar situation we talked about previously. Over here is the other space, and any x from here, if x is one of your vectors, okay, if this is an x, any x from here has to end up in here. Now, your b vector, this vector, well, this vector has 5 components. Now, any x over here is also going to have 5 components, but this is only a 3-dimensional subspace. Okay? So, this is your column space of the matrix A, has dimension 3, and it's the row space of A transpose. This is orthogonal to your column space. It's the null space of A transpose. It has dimension 2 because, of course, the dimension of the row space and the dimension of the column space have to add up to the dimension of the whole space. So, the B vector is somewhere in R5. There's no expectation that it's going to be in this 3-dimensional subspace. We don't have any restriction on these numbers. What we want to find is, we want to find the vector in this space that's as close as possible to the B vector. Now, I haven't written it out, but the B vector is unlikely to be in the column space, so B is going to equal if B equals AX plus some vector in this space, it's going to turn out that this vector has to be in the null space. Okay, so we have the picture. Okay, we have our B. We have our B row. A vector in the row space of A transpose, and our B sub n. Okay, there's a unique B sub row and a unique B sub n that equals B. That means then that the x that we want is the one that maps to this B sub row. Now, I haven't had room to write that down. It's going to come down to this, though, that remember B is uniquely equal to B sub n plus B sub row. and this b sub rho is the ax that we want. It's the vector in the row space that's closest to the vector b, because this vector turns out to be the projection of b onto the row space. Now, I'll say more about that, but that's where we are, and we don't necessarily completely understand this, but we'll develop this idea. So that the x that we want is the one that maps to b sub rho. Okay, the desired x vector is the one that maps to b sub rho. Now again, we'll talk more about that. Don't have room to do it here, but let's accept that for the moment, and then we'll justify it a little bit later. But let's see where that leads us.